We're going to continue our discussion about the deflection of beams by taking a look at what's called matching boundary conditions. Before we get into that, let's just review a little bit of what we already know about beam deflection. We started with the deflection curvature relation, m is equal to EI over rho, where m is the internal bending moment in the beam. E and I is the bending stiffness of the beam, which is the product of the modulus of elasticity, the material stiffness, and the cross-sectional stiffness, or the moment of inertia I, divided by the radius of curvature rho. Now 1 over the radius of curvature we saw from class previously turns out to be approximately equal to V double prime, where V is the deflection curve equation. V prime turns out to be approximately equal to the slope of the beam, theta. And so when we put all of this together, we end up with this equation that says EIV double prime is equal to m. And if E and I are constant, when we integrate this, then we can have EIV prime, which is the slope, is equal to 1 integral of the moment equation. As an indefinite integral, that gives us 1 constant of integration. And when we integrate it again, we have the deflection V, which is the integral of what we had previously, with a second constant of integration. And the constants of integration come from our boundary conditions of our beam. And just as a review, we looked at a couple different types. We had a simply supported beam. I'm just going to put some load on it. The load is irrelevant to the boundary conditions. But if the length of the beam was L and we start our coordinate system on the left side, then at the simple supports at x equal to 0, there is no deflection. And on the right side at x equal to L, we also have no deflection. For a cantilevered beam, where it's fixed on one end, if the length of the beam is L and my coordinate system starts at the wall, then I would write down x equal to 0, v is equal to 0, and x equal to 0, v prime is equal to 0, because I have no slope at the wall, and the deflection curve would take some sort of shape like this. In this case, we talked about how you can find the maximum deflection by looking at the end of the interval or to the end of the beam. And in this case, the deflection curve might look something like this, where the maximum deflection occurs where the slope is 0 in this case, or the derivative, but the slope is not 0 on the left and right sides, as we can see from this picture. Now, what distinguishes what we did last time from what we're going to do this time is that in these two cases that I just drew, all we had to have is one moment equation for the beam. In other cases, there are more than one moment equations that we might have to find. And let me demonstrate this with a fairly simple example of a beam with a load in the middle. If I were to sketch the reactions for this beam, determine those from statics, this would turn out to be P over 2 and P over 2. And my shear force diagram would jump up by P over 2, would go constant, jump down by the amount of P, and then come up here. And my shear force, my bending moment diagram would have a straight line that slopes up to that point, and then a different straight line that slopes down back to 0. And so the point of this is that I cannot have one equation that describes both of these line segments. There are two different lines, two different equations, M1 and M2. So what we're going to have to do is we're going to have to break this beam up into two different regions. Region 1, that will go from x equal to 0 to L over 2, and region 2, that'll go from L over 2 to the end of the beam L. Let me sketch this picture again on the next page, and we'll work this problem out as an example to illustrate what we're talking about with this idea of discontinuous moment equations. All right, so here I have my beam. I just redrew that with the free body diagram, and I'm going to break these up into these two regions. On the left of my panel, I have 0 to x to L over 2, and on the right, I'm going to look at L over 2 to x to L. So I want to draw the free body diagram, and in this case, I'm going to draw the free body diagram. I'm going to look to the left of my cut. On the left of my cut, I have my force reaction of P over 2. I have a distance of x to the cut. It's very important that you have a variable distance x. And on the cut, I have my shear force and my bending moment that I'm going to draw in their positive directions. And I want to make it clear that I'm looking at region 1, so I'm going to label this as V1 and M1. So if I do the summation of moments about point O, I will have M1 minus P over 2 times x equal to 0, or M1 is equal to P over 2 times x. Let's do the same thing. Let's find the moment inside of region 2. And on my cut, the distance from my origin to my cut spot is still the variable distance x. And I have a choice of looking at to the left of the cut or to the right. In this case, I am going to look to the right of my cut because I have fewer terms to deal with. If the beam's in equilibrium, it doesn't matter, but the algebra is just a little bit less involved. Now, what that also means, though, is that the distance from the cut to the right side of the beam is L minus x. And my shear force and my bending moment in their positive directions look like that. Compression on the top for my bending moment, and that's V2 and M2, because I'm in region 2. So let's do the summation of moments about that cut spot, and we'll find out what M2 is equal to. So I'm going to have minus M2 plus P over 2 times the distance L minus x equal to 0. If I solve this for M2, it's going to be equal to P over 2 times L minus x, that quantity. And if I want, I can expand that out, and I'm going to go ahead and do that in this case. P over 2 times L minus P x over 2. Now, since the moment equation is discontinuous, we have two separate moment equations, we're going to have to set this up as if we have two different deflection equations. Oops. In my first region, I have EIV prime, double prime 1 is equal to M1. And in this one, I have EIV2 double prime is equal to M2. And I'm going to integrate both of these up. So EIV1 prime is going to be equal to P over 2, x squared over 2 plus 1 constant of integration. And EIV1 is equal to P over 2, x cubed over 6 plus C1x plus C2. Over here, I'm going to have EIV2 prime is equal to P over 2 Lx minus P x squared over 2 times 2 plus another constant of integration that I'm going to call C3. Integrate it again. P over 2 L x squared over 2 minus P x cubed over 2 times 6 plus C3x plus another constant of integration, C4. Now we need to figure out what our constants of integration are, and we need a boundary condition for each constant of integration. If we go back and look at the original picture of our beam, here was the coordinate system plus x was to the right. We have a simple support situation, so at x equal to 0, we do not have any deflection. And at x equal to L, we do not have any deflection. But we have to be a little bit careful here. This support lies in region 1, and the other support, the roller, lies in region 2. So we need to be very specific now. At x equal to 0, V1 is equal to 0, and at x equal to L, V2 is equal to 0. Since we have 4 constants of integration now, we need to have 4 boundary conditions. This is what are known as matching boundary conditions. If we look at the boundary point, it doesn't have to be under the load, but it's wherever the boundary between region 1 and region 2 is. There's a couple things that have to happen in order to preserve what's called continuity of the beam. At x equal to L over 2, the deflection from region 1 has to equal to the deflection of region 2. If it didn't, then the beam would not have a continuous displacement in the vertical direction. It would be like the beam would be broken. In addition to the deflection condition, we also have a condition on slope. The slopes evaluated at that specific spot have to be the same. So at x equal to L over 2, we have V1 prime equal to V2 prime. Now the way I usually write this is, since we have the E and I that's kind of been carrying along with the terms, I'll write this as EI V1 is equal to EI V2, and EI V1 prime is equal to EI V2 prime. These are known as the matching boundary conditions. So let's plug in some of our boundary conditions. We'll see what we can fit on this page. So over here in region 1, I have x equal to 0 and V1 is equal to 0. Means I can plug that into this equation. Put in 0 for V1, put in 0 for x. That tells me that C2 is equal to 0. Over here, I have x equal to L, V2 is equal to 0. So I plug in 0 for V2, and I plug in L for x. I'm going to get a PL cubed over 4 minus, here we have a PL cubed over, let's see, that would be 12 plus C3 times L plus C4. Notice I have 2 unknowns in this equation. Okay, now what I'm going to do is I'm going to go to my slope equation, and I'm going to set EIV1 equal to EIV2 when they're both evaluated at the particular position x equal to L over 2. All right, so over here I'm going to have P over 2 times L over 2 quantity squared divided by 2 plus C1. And I'm going to set that equal to EIV2 prime evaluated at x equal to L over 2, which is P over 2 L times L over 2 minus P over 4 L over 2 squared plus C3. Okay. Those two are going to be equal to each other. And then I'm going to do the same thing with the deflection equation. EIV1 evaluated at x equal to L over 2. So now I'll have P over 2, L over 2 cubed over 6 plus C1 times L over 2 plus C2, but we already know that's equal to 0. is going to be equal to EIV2 evaluated at x equal to L over 2, which is going to be equal to P over 2 times L over 2 quantity squared divided by 2 minus P times L over 2 cubed over 12 plus C3 times L over 2 plus C4. All right. Let me rewrite these equations on a new page, and then we'll talk about what we're going to do to be able to find C1, C2, C3, and C4. All right, so after applying those boundary conditions, we got these 4 equations, and I just wrote down the equations that we had on the previous page. We have C2 is equal to 0, so that's good. We know what C2 is for sure. But we have unknown C3, C4, and C1. But what we have now are 3 equations. And we're going to solve 3 equations for 3 unknowns. C1, C3, and C4. Now the algebra here can be very tedious. For your homework problems, you only have a couple homework problems on matching boundary conditions. I want you to go ahead and answer the problem that the book is asking you. That means go and do all the algebra. It's good practice to go ahead and do that. On an exam, I will have you stop at this point if I give you a matching boundary condition problem. You will not have to do the algebra on the exam. So let's make this clear. There's a couple if statements here. If you have a matching boundary condition problem, I will have you stop let's make sure this is clear on a test. If you have a matching boundary condition problem on a test, I will have you stop after you set up your equations by applying support boundary conditions and matching boundary conditions. For homework, grind it out. Now, after you find your constants of integration, you can plug those back into the respective slope and deflection equations, V prime and V equations, and you can find your slope and deflection in region 1 and region 2. You can find maximums in region 1 and region 2 and answer all the same kind of questions that you can be asked about one region beam problems. The concepts are very similar between 1 and 2 region beam problems, except we have this matching boundary condition situation. Let's kind of review the steps. All right, so to kind of review a little bit, here's a beam, and if your load is discontinuous, all right, so I had a couple interruptions there. If the load happens to be discontinuous, such as in this case with a simply supported beam, what you have to do is you have to break this beam up into 2 regions. Sometimes this is in the middle of the beam, sometimes it's in different spots. For this example, let's just say this is the distance L over 3 where this load stops. You would cut inside region 1, and you would find from a free body diagram in region 1 your internal bending moment for section 1. And then you would set that to EIV double prime. You would integrate that twice. You would end up with two constants of integration, C1 and C2. You would make a cut inside section 2, looking in either the left or the right side. And you would go through the process and you find your M2, and you set that to equal to EIV2 double prime, integrate it twice, and you get two additional constants of integration, C3 and C4. In order to find these constants of integration, you look at the support boundary conditions. In this case, x equal to 0, V1 would be equal to 0, and over here, x equal to L, V2 is equal to 0. And then you look at the matching boundary conditions, and the matching boundary conditions state that the slope and deflection at the boundary point, which in this case is L over 3, have to be equal for region 1 and region 2. Okay, there it is for the slope, and here it is for the deflection. Try to emphasize that it's in region 1 and region 2. Now you could do additional regions. You could have as many regions as you needed. However, the algebra for this is bad enough. I would never give you more than 2 regions to apply matching boundary conditions. This would give us 1, 2, 3, 4 equations. Oftentimes 1, sometimes 2 of these constants of integration will be 0, but it could be as bad as 4 equations and 4 unknowns. On an exam, just to say this again, on an exam, I would stop you after you have applied the boundary conditions and gotten the equations. That doesn't mean just writing this down. That means actually putting in x equal to L over 3 into the equations as appropriate, or whatever the boundary point is. Listing out those equations that you would need to solve for the constant of integration. For your homework, go ahead and solve it all out. I'm going to try to make a separate video where I go through a homework problem.